the page. Maybe I can do that with this. Uh, Sorry for the technical problem again. Okay, okay, now it works. So as you probably know, Bayesian models can mean two very different things. Here are two great textbooks. The left one is one of my favorite Bayesian modeling book. It's about how you fit and build, fit, and compare models with in Bayesian statistics. And this is not what we are going to talk today. What we are going to talk today is closer to the right one. So to discriminate from the left one, we like to call it Bayesian observer models. So here's the outline of today's talk. And we'll start with the question, what are Bayesian observers? This is probably one of your most familiar formula in statistics, the Bayes theorem. And the painting on the right side, you see there's Thomas Bayes, but with the question mark in the parentheses. Why? Because we do not exactly know whether this is Bayes or not. So it's kind of a famous joke that given your knowledge, what do you think, what's your posterior probability estimate for this is the painting for Thomas Bayes? Okay, and this equation actually have many variants. Like you probably see in the paper, many papers use this form. So what it does is to just ignore what's in the denominator. So and to replace it with a proportional to mark here. And what I like to do, or what I prefer, is to give all of this some kind of meanings, so it's easier to remember. So how about um, sorry, I think this is still too inconvenient. Uh, okay, let's take some risk. So if we use this special case, so suppose we are going to estimate the probability of one specific hypothesis, Hi is holds. It's proportional to the likelihood that if Hi is correct, then your probability of observing the data X. So this is likelihood times the probability, the prior probability of the hypothesis I. So this makes much sense to me. And we are going to do some practice to see how we could solve a problem using this Bayes theorem. It's actually kind of famous. So it's called the Monty Hall problem. Monty Hall was host of a famous TV show in Canada. And what's the show look like? It's like every time some guests were invited and Monty Hall would show him or her 3 doors. And the rule is behind one of the door, there is a car. And the other 2 doors would be one goat. So if you happen to choose a door that hides the car, then you would get the car. Very happy to go. But if you choose a door with a goat, then you get nothing. No, you don't get the goats either. So the guest, what the guest could do is to choose first which door would you like to open. But after the guest makes their choice, they do not immediately see the results. Instead, what Monty Hall would do is to open. So there are two other doors the guest does not choose. So Monty Hall would open one of these doors and to reveal a goat. So he always reveals goat. He would not reveal any car. And then he would ask the guest, okay, here is an opportunity. You could choose to switch to the other door that had not been opened. Would you like to switch or not? So this is the choice you are going to make. Will you choose to switch if you were the guest? Did you say no? Yes. So why? Tell us. So you say you will or you won't?
I won't.
You won't.
Yes.
So the answer is no.
Yeah.
Is there any other? You're very typical. A kind of very typical error. I made the same error before. Yeah, I first time when I heard the problem, I made the same error. Actually, even some statisticians made the error. But do you have any other answers? So obviously, the correct answer, I mean, uh, now I tell you that you should switch. So you come with other reasoning.
Why would you switch?
So if I tell you switch is correct, can you figure out why you should switch?
I think the conditional probability given you choose the goat one of the choose the goat. I think the probability to get the car will increase to I think is two 1 second. Yeah. So I will change. Yeah.
I think you are correct in predicting that the probability increases, but not to the correct value. The correct answer is 2/3. Um, you can find many different solutions to this problem on the internet. There are actually, if you search the Monty Hall problem, you can find numerous videos to solve the problem. But here, what I like to use this problem to illustrate that is actually all kinds of such probability problem. It can be solved by the Bayes theorem. And so in other words, if you try to solve something in probability and you know all the probability of the events, you have the assumption that every event can be assigned to a probability, then the only correct thing to do is use a Bayes theorem. So I think here the trap is why the first time, like many of us thought, oh, it's the same 1/3, nothing changes, because you think the host just randomly choose one door. No, it's not randomly choose. this does have some information. If the other two doors all contain the goat, each contains a goat, then it's randomly choose. But suppose the other two doors, one of them contains a car, the car, then the host will not reveal the car, but to reveal the goat. So this means what the ghost does is kind of provide you with some data. So let's look at this problem from the Bayesian perspective. To make things simple, let's just assume just you choose the first door at very beginning. And then the host opens the third door. And here comes the goat. So let's frame it in the Bayesian way. Look at what's the prior, what's the likelihood, and what's the posterior. The prior probability, so just to make sure, what we'd like to know is the probability that each door contains the car. Okay, so at the very beginning, the prior probability means before you see what the host does, then the prior probability for the first door to contain the car is 1/3. And it's the same for the second door and for the third door. And this is what all of us agree on. And then comes the move of the host. And from the host, what we can see is what's the likelihood for the host to open the third door. So we use the host equals 3 means host opens door 3. So if the car is in the first door, then the host opens the third door. It's just one half, because he could either open the door 2 or door 3. But instead, if the car is behind the door 2, then the probability for the host to open door 3 is certain. It's 1. And of course, if car is 3 and you open the door 3, it's 0. Well, our basic assumption is you choose the door 1. So there are only 2 doors left to the host open. Like the host will not open the door you choose. The host will not either open a door that contains a car. So if you choose a 1, then yeah, what the host could choose is either 2 or 3. And if the car is behind the 2, then the host will not open the 2. What he'll open is 3. So this is certain. And this is what the information is. So now you could compute the posterior. So for now, what we could
the speaker was muted. Han was muted. We don't hear her. We can see on Zoom that her channel was muted. It's not the microphone, it's Zoom.
Use this one.
Yeah. Thanks.
Okay, yes, now it's good. Thank you.
Sorry for so many technical issues. Okay, a good fight back from Beida. Okay, so what we would like to know is, given that the host opens door 3, then what's the probability that the car is behind the door 1 instead of door 2? So as we know, this posterior is just sorry, the slides I can't. Oh, okay. Okay. So it's just likelihood ratio times the prior odds. So you just serve the numbers you have already had, and what you get is 1 to 2. That means if you switch to the door 2, then your probability of winning the car would be twice if you don't switch. So the probability you win the car if you switch would be 2/3. Okay. So this concludes the Monty Hall problem, but I'm also going to use this Monty Hall problem to illustrate what Bayesian observers. So we already have the first part. Bayesian observer means you are doing inference following Bayes' theorem, but that's just the first part. And the second part would be after you kept the information, you would act or choose according to what you think to maximize your expected gain. So suppose now we already know the answer. You know the probability of choosing not switch and switch would be 1/3 or 2/3 to win the car. So what would you choose? It depends on, okay, what's the bonus? So here is actually obvious. So what you could choose is to switch or not switch. So stay on 1 or switch to 2. And what's the outcome? We have a matrix. So if it's kind of obvious that if the car is in the first door, then if you stay on 1, you will get the car. And if it's in the second door, then you switch 2, you get a car. So what we have for the 2 possible options are actually lotteries. So it means if you stay on 1, then you have a 1/3 probability to win the car and 2/3 of probability to win nothing. And if you switch, here's the lottery. In this case, it's actually quite obvious that the switch to 2 it dominates the state on 1. Just nothing. If you are just rational, if you would like to maximize your probability, either your probability of winning or your expected gain is just the same. But suppose we add a new rule. Now it's not free to switch. You need to pay $100 to switch. Then what would you choose? So the probability would not change. It's still 1/3 and 2/3. But now your payoff matrix will change. So you will see the -100 reflected in the table. So you face 2 very different lotteries. So what would you do? If you believe that a car is at least like it's worth I think more than $200 or $300. 300.
You'd be surprised how cheap cars can get.
Oh, okay. I thought about set the value to 10. Okay, that would make it fair. Um, I saw like the car in the TV shows, like the Breaking Bad. They sell the car for 50, but it kind of they're trying to conceal like some they are criminals. They're just trying to yeah. Okay. So if we think reasonably, like a car at least like say worth at least $1,000. Okay, let's go with it. Okay, if you believe that it's at least more than $300, then your best choice is still switch to two. If we still think that the car worth is more than $300, but what about your decision rule changes? Not everyone tries to maximize expected gain. Some people think about the worst. So you guys probably hear about the maximin or minimax. They are the same. You are trying to maximize your minimum gain. Mini-max means you are trying to maximize your max loss. So if you think in this way, then you probably should choose to stay on one. Because if you switch to two and you don't get the car, then your payoff would be minus 100. That's the worst. And if you stay on one, what's worst would not be worse than zero. So this is what we mean by Bayesian. Minimax is kind of an alternative choice rule to Bayesian. And of course, you can think about numerous ways to deviate from Bayesian. We'll see some examples later. Like if you simply just, I know the probability, but I have no interest to maximize my payoff. Okay. So you already touched the Bayesian decision theory, and I'd like to use an example to illustrate it more formally. Bayesian decision theory is a normative theory on how to act under uncertainty. So this is very general. If we can summarize it in just one scheme, it would look like this. You have some stimulus from the environment, and you are trying to estimate the generator model behind it following the Bayes theorem. So you combine the prior with the likelihood and get the posterior. And then you consider the payoff matrix, the gain function, and you combine it with the probability you have just computed. And then you will, based on this, would act based on this. What you would do is select action rule maximizing base gain. So here's come out many notations, but I'm not going to introduce them here because we will come step by step next. I will use the signal detection problem to illustrate the Bayesian decision theory. I know Tianmin already covered it a few days ago, but I will from very different perspective. So I hope the overlap is minimal. As you know, many problems in our life can be framed as kind of signal versus noise, or just a binary choice. So you see a stimulus and you're trying to detect whether it's a signal or noise. it could vary in very different forms. Like for a doctor or radiologist, like when reading such a CT scan, the doctor would wonder, is this a tumor or not? And if you are collecting mushrooms from the wild, you probably want to know, is this mushroom poisonous or edible? And when you are in the court, the judge or the jury would like to judge whether the suspect is guilty or innocent. Actually, there was also an example coming from our lunch, today's lunch, like we talk about how could you judge whether a reference letter is convincing or not. So I think we could think about all these kind of problems as kind of urn problem. So you have two urns, a black urn and a white urn. They have different proportions of the black and the white balls. So this as a hidden hypothesis is behind. Both of them could be, either of them would be choose to generate some samples. And what we have are samples. And in this kind of signal detection problem, what we need to do is to, based on these samples, to get a probability, posterior probability of what, how likely it come from the black urn or the white urn. So this is just a very general problem. I use this one to just analog for almost everything. Okay. And this is probably what you have seen again and again when we talk about the signal detection theory. You see two Gaussian and they have some overlap. What happened? Okay. So the x-axis, it could be the decision variable, and the y-axis is a likelihood. Or here we use the f to denote the probability that if given a state of the world, we use the w to denote the state of the world. What's the probability or probability density of observing a specific x? So suppose our problem here is to judge whether some suspicious tissue, whether it's tumor or not. We can think about in a very just oversimplifies it. As far as I know, very limited medical knowledge that if it's the larger it is, the more likely it would be a tumor. So let's think about like x-axis is how large the suspicious tissue is. So suppose we have some of this observation xt here. And with this kind of plot, we could easily get what's the, wait, okay, I got it. If I press this key for a long time, then it will trigger something. So the likelihood here, so given the x, what's the likelihood of the word is w? So here the w could be s, the signal, or s bar, the noise. It's simply the f. Okay. But what I'm going to illustrate here is the likelihood function do not necessarily to be Gaussian. They can be everything. So think about mushroom. I think when I was young, I got some knowledge that if a mushroom is too colorful, it's likely to be poisonous. But later I learned that this is just oversimplified. And of course, we know more about like whether a suspect is innocent or guilty. It's also complicated. Some guilty people can pretend to be very innocent, and it could be also be the reverse. So to illustrate this kind of complexity, I draw these curves with my hand. So it can not be very precise. I'm trying to keep the area below them look almost the same, but I can't promise that's exactly the same. So suppose we just get this kind of thing. Does signal detection theory still work? Yes. Signal detection theory actually does not care about what the likelihood function is. It could be anything. So you can draw the same line here and get them the similar likelihood here. Okay, now we have the likelihood set. Then let's look at the second part, the gain function. Oh, I'm so happy the bar on the S shows correctly. They don't show correctly on my own computer. I think this is a projector's problem. Okay, and so in the signal detection theory, our choice is only two. It's either you choose this is a signal or it's a noise. So we would the small letter S to denote the action of this is a signal, and the S bar to denote this is a noise. So this would be the action, and the capital letters would be used to denote the word of the state, whether the word is really, this signal is really, whether this stimulus is really a signal or it's a noise. And the gain function is a function of the action and the word. Very fair. So this is probably what you saw most for signal detection theory. We know the four quadrants. This is called a hit. And this is called false alarm. And this is a miss. And this is correct rejection. And usually, if we just reward accurate response, then it's 1 for a hit, 1 for correct rejection, and 0 for the other two incorrect answers. So in this special case, maximizing gain equals maximizing accuracy. But this is just a special case. How about we change it a little bit? Suppose now we change this cell from 0 to 1. What does it mean? You simply would not be penalized for false alarm, right? And in this situation, you will see that to choose action of S will dominate S bar. And it means no matter whether the word is S, whether it's a signal or noise, choosing, you say this is a signal, is always the best or equally good choice. So now you see what's the optimal choice depend on not only the probabilities, but also on the gain function. And a very usual case could be like this. So it's like, again, this table is asymmetric. You could have 0 for false alarm, but could get -1 or even worse for miss. For example, in the case of the detection of tumor, miss is probably more terrible than the just false alarm. And in general, we could write the gain functions like in this way. Okay, so we have settled with the gain function, and the last missing piece would be the prior. So it's a probability we believe is signal or the noise. And in this case, of course, they should add up to 1. For Bayesian decision theory, actually, is to decide a decision rule. A decision rule means it's a mapping from stimulus to action. So what kind of mapping would you choose to maximize the base gain defined like this? A easier way to think about this is for each specific X, you choose the best action, or you choose the action to maximize this. It's quite intuitive. Actually, this is a formula you may derive for yourself. It kind of easy to derive that if you want to maximize expected gain, so what should you do? What criterion should do? This kind of general formula we have. And I think the way I write it here, maybe not a very conventional. A more conventional way, maybe to move the likelihood to the left side. So you just choose, so what kind of likelihood I get, then I will choose it's a X, it's a signal or it's a noise, but the effect is the same. And why I like to put a stimulus here, formula here, because I think it's kind of, what could read from here is, as you can see, the prior and the gain function, they play similar roles. To change what a Bayesian observer does, you could either change the prior or the gain function. Okay, now come to the 10 point that I will challenge you. So suppose there's a person on the AI. I mean, it does not come to me as very different as soon as we consider them as a Bayesian observer or not, because we only care about I think Rava had introduced in the introduction every time that this is a computational theory level, so we don't care how it's implemented. So we just think about there's the agent, and the agent we give, like, say 10 or 20 or 100 mushroom pictures to the agent, and for everyone the agent judges this to be poisonous. My question is, could this observer be a Bayesian observer? What do you think are the possibilities? And what future tests could we do if we'd like to know whether the agent is Bayesian or not? So you can think about any possible reasons you could explain the observer's behavior. So we have an observer, and the observer judges the every mushroom pictures, mushroom is poisonous instead of editable.
One of my colleagues doesn't eat mushrooms, so
Okay.
it's gotta be.
Okay, so what you mean are the gain functions?
Yeah, that's right.
Okay.
So that's one.
Okay. Yeah. This is from the gain function side.
Maybe this agent think all the mushrooms is poisonous. The prior, it's
Good.
prior
Good. This is
from the prior side.
second one. So we start with gain functions. Now come to prior. Maybe the agent. So I'm kind of curious. Actually, if one holds a very strong prior, as strong as he or she will never change it, it could still be categorized as Bayesian, right? Yeah.
Yeah.
Just to extend this line of thought, either the prior is so strong, it could also be, it's very strong, but not necessarily like never change. So if in the last 100 years, the agent has seen, the mushrooms agent has seen are all poisonous, then the agent may build a prior for this. Like it's very likely. So your only 10, 20, or 100 observations would not change the prior. And any other thoughts?
Any thoughts on the basil side? A lot of people like mushrooms.
Okay. Actually, of course, the observer could well be non-Bayesian. Like, yeah, just produce some nonsense responses.
Mhm.
And this could, all of this could be possibilities you encounter in your experiments, say with humans or animals or with your networks, the behavior of your network. I think all of these are possible. So any idea what future tests could we do?
It is unmuted, yes. So we have an answer here.
Hi, we could take a non-poisonous mushroom and force feed it to the person. And if the person then adapts the posterior to then classify that mushroom as non-poisonous, then we could expect that it's a Bayesian observer. But if the person still keeps classifying that mushroom as poisonous, then it's probably not. Did that make sense?
Sorry, I can't hear you very clear, but I guess your answer would be correct.
She has extremely good priors.
Yeah, so the general the general trick is just you can either use some way to try to change the agent's prior belief or the gain function. And usually the gain function is a quicker way because you can change, say, so as Louis told us, like he had a colleague who can't
Will not eat
mushrooms.
mushrooms, yes.
Yeah.
So I
we
can trick them.
switch to a different colleague who like mushroom.
I was trying to trick Jackson by telling him it's not mushroom and hide it in some food. Anyway, that's probably not a good idea.
Oh, okay. Okay, let's continue. So our question is, are humans Bayesian? I would like to show you two variants of Bayesian observer model today, and we'll have one. Oh, it's fine. Okay, we can take a break here.
Introduce the two, and
So
then
it's time to break, right?
up to you. I think we can take a break.
I think we can take a break here.
Okay.
Yeah, it's fine.
Yeah. Okay. Let's take a short break. And then we'll be back in what time? 10 minutes. Okay. So I have 6:33. Okay. Let's get started again.
Okay.
Oh, sorry.
The first example I'm going to use is from the paper by Wozni et al. 2010. And it's a hierarchical Bayesian observer. Their task actually is easy. It's they would show participant two cues, a sound and a visual cue. And the participant need to do is to judge where the sound come from. They don't need to judge where is the visual thing, because we have very accurate estimate of the visual stimulus, right? And their hypothesis is, we know in the case that something is uncertain, like you have a noisy stimulus, then you are trying to combine information from other channels to get a even better estimate of this, like in this case, the location of this stimulus. So suppose some object or some person makes the visual image and the sound, so they have the same source, then you could use the visual stimulus to combine the visual and the auditory information together to get a more precise estimate. It's called Q combination. The problem here is participants may not assume these two kind of things come from the same source. So suppose you see, say, some sound appears here, but you see the visual image here. Then you probably think, oh, they are so different, they can't be the same. What I'm trying to describe is maybe some kind of computations happening in your mind or in your brain, not you explicitly perceive that that's possible. And in this study, they try to capture this kind of computations and figure out what people would do in this situation. So they built a hierarchical model. So whenever we talk about Bayesian observers, we will start from the generative model. This is about how the stimulus you observe may be generated. So assume there are two probabilities. This C means whether there is one categories or the two categories, or we say one source or two sources. So the left side is suppose the sound and the visual image come from the same source. And the right side is the other probability. They come from separate sources. And what the observer need to do is to, based on the stimuli they observe, to infer the probabilities of these two probabilities. And in this plot, they give example of suppose they compute the probability that they come from the same source is 0.3, and the visual and auditory stimuli come from two different sources are 0.7. So this is basically just a kind of typical generated model, and the Bayesian inference is not difficult. What I think this example is instructive is they assume several ways of response. So after an observer gets such kind of probabilities, what response would this observer make? They consider three possible decision strategies. The first decision strategy is called model averaging. It's connected to the model averaging in machine learning. So I'm just assuming many of you have experience working with models. So you test two models on the same data and you find, oh, okay, this one has an AIC of say 10, the other has an AIC of 5. Then if you make say, oh, the best model could maybe either this one or that one, then you can compute a weight of how likely model 1 to be the best model or the model 2 to be best model. And one thing you could do is say, oh, then I'll just choose the best model from these two guys. And this is called the model selection. The other way to do this, if you don't care about, I don't want to know which model is best. My goal is not to choose the best model. My goal is to make the best prediction. Then what you can do is you could average these two models. You could average the predictions from these two models based on their weight or how reliable they are. So this is model averaging. By model averaging, in this case, you would use 0.7, give the 0.7 weight to the one source hypothesis and 0.3, sorry. I just found their plot as so confusing. They just reverse the left and right side. Okay. Okay, but you know it is either 7.7 or 7.3. So you average these two predictions and get your estimate of the position of the auditory stimulus, the SA hat here. So this is model averaging, and the model selection we already know. You just choose the best hypothesis. Here is the 0.71. Is there are two separate sources. And the third possibilities I already learned how to fix this problem. And the third probability is it's called probability matching. It's like the observer would choose 0.7 to choose this one, two separate sources, and 0.3 to choose one source. What I'd like to point out here is actually the first two decision strategies, they are kind of Bayesian, but the third is not. So for the first one, the model averaging, if you are trying to minimize the expected square error of your final estimate, then model averaging is the best thing to do. It would be easy to prove this, and you probably have already know this. Like, so if you want to minimize the expected error, then the mean would be the best choice for many things. And if you are going to maximize the probability of choose the correct codal structure, one source or two sources, then model selection is the best thing to do. But the third one actually is a suboptimal. The only reason to consider it, of course, is because it fits the data. But it also has a very long history, findings from animals and also humans, that we may sometimes choose from two options that's based on the probability they are going to be correct. I'm not going to explain this kind of reasoning, like whether probability matching is really suboptimal or not. It's just from the Bayesian perspective, it's suboptimal, but it could be optimal from a higher level reasoning. Like if you think the world is changing, like there's something hidden there I'm trying to learn, then, but in this case, I don't think it fits in this case. In some cases, it does. So we just go on to show what they would do. So the first thing to do is to build the models, and we already have the models. And the second thing they do is to show what these three kind of decision strategies would predict. So the first line, second row, and third row, they are respectively averaging, selection, and matching. A big difference you could read from the first row to the, say, this one, averaging, you'd see. So the different columns are from different conditions. Like the first column, you have the visual and auditory stimulus just at the same place. And to the right side, you will see a bigger and bigger difference between them. But as you can see, the averaging decision strategy would predict a very continuous distribution of responses. However, the selection one or the matching one, they would have some different pattern. And this is kind of like visualization of the predictions. And they also did formal model fitting and comparison, and found that most of their participants was best fit by the matching model, 75%. So I was trying to use this example to show that what you can do with the Bayesian models is you could frame a Bayesian model, but you could add something that's not so Bayesian, like some decision bias. It's not a Bayesian observer after you add the bias, but it still have some connection with a Bayesian, and you can look at as a kind of ways to expand the way you can explain the data patterns of the human or animal observers. Okay, so finally we come to the break time I formally set up. We should start here. And the second example is a classical paper by John Anderson in 1991. It's about how people do categorization. And very influential idea Anderson proposed is human categorize their observations in a rational way. So why do I choose this example? Because it could illustrate a very important part of Bayesian inference. as we know, when we say a Bayesian observer, we always come with some very specific generative model. So when you say a Bayesian observer, you must associate with it with a specific generative model. And for most Bayesian models, it may look like this. So it has finite latent structures. Like in our example before, there was either one source or two sources, or as it goes with the signal detection theory, it's either signal or noise. It's finite. But humans may invent new categories as needed. For example, when we try to organize our ideas with a note app, say we may come with new tags. From time to time, we're not restricted to say I can just use these 2 tags, the 3 tags. We can add new tags. The computational challenge here is how can Bayesian observers introduce new categories on the fly? The typical one was you have finite number of categories. A very useful thing is the Chinese restaurant process. It's a special case of the Dirichlet process. It's a stochastic process to generate infinite categories. So let's see. It's a basic idea we will see is that a rich gets richer. So the problem is like this. It's called a Chinese restaurant process because I know in China it's not usual, but in Chinese restaurants in America, like in New York City, they have some very big round table. And when you come, and if you come alone or just a few friends, you may be assigned to a big table, and later some other guests come. They may join your table. You are not a group, but you share a table. So the name comes from such analog. So suppose there is a Chinese restaurant, and I think I should use pointer here, right? So, and in this restaurant, there are many tables. Actually, the number of tables could go to infinity. And let's call this table 1, table 2, table 3, and table 4. So the problem here is if table 1 has 4 guests, 4 customers, and the table 2 has 3 customers, and table 3 has 1 customers, and other tables has no customers. And here comes a new customer. Which table will the customer join? I know if it's me, I will choose empty table. But this is not the analog would like to imply. So the idea here is the rich get richer. So this table is an analog for the category. If a category could be a analog for the category. So if a category has many members, then it can have a higher probability to attract more members. So the equations goes like this. If you already have n customers from 1 to n, and their tables are denoted by the 1 to the n, and then when it comes n plus 1 customer, then its probability to be assigned to a specific table J would be, if J is an existing table, then is proportional to the number of customers already on the table, the nj. And if j is a new table, then it's proportional to a constant alpha. It's called concentration parameter. So let's see how it works. Let's just assume alpha equals 1, just for easy to compute by hand. Then it's easy to see table 1, table 2, table 3, they are existing tables. So you would have, this would be 4 divided by 1 plus 8 would be 4/9. And the table 2 would be 3 divided by 1 plus 8 would be 1/3. And it goes like this way. So how could we use the CRP as a process to solve our problem of creating potentially infinite categories? What we are going to use CRP here is use CRP as a prior, as a distribution over distributions. Let me show you how the intuition goes. So a different way to look at the same problem is, now we still assume alpha equals 1, and we only care about how many customers are there on a specific table. So when the first customer comes, of course, the customer could only go to the one new table. So there's one table with a customer, one customer. And then comes the second customer. Then there would be two possibilities, either to the existing table, the table 1, or a new table. And as our equations would imply, this would be 1/2 and 1/2 probability, right? And if now comes a third customer, then you can compute what's the probabilities of these different possibilities. Or for the second possibility, if there comes a third customer, how it goes. So now, if up to here, you have 3 customers, then you could see what's the probability, what are the probabilities associated with these different possibilities. You can come with the probability, the numbers of the probabilities. So as you can see, the CRP actually, it implies a distribution over the distribution of customers over the tables. So these are, each of these possibilities is one distribution, and the CRP prior is a distribution over these distributions. Okay. So how could this CRP prior goes into the categorization? So first, we need to, as for every Bayesian model, Bayesian observer model, we need some generative process. Again, we use the tables, but now we would use such kind of a bar. So this bar, each bar has 5 cells. It denotes you have 5. Each of the stimulus has 5 dimensions, and on each dimension is a binary value. So it's 0 is either 0 or 1. We would black to denote 0 and the white to denote 1. So you can see each of these bars here is a vector of 0 and 1. So we could start from there's no stimulus here, but it's equally instructive to consider as before that we have a new, how we can generate a new stimulus. there are two possibilities. As we know, one possibility is we may generate a stimulus from an existing table or an existing category. Oh, one thing I forgot to mention is each table actually associated with a stereotype. Sorry, I'm not sure whether I got the right word. Okay. Okay, never mind. You just have a prototype. Sorry. Yeah, prototype. It means we can forget the word either. It just suppose there are some real values behind this table. Like each stimulus generated from this table will be a sample from these real values. Like say we are going to generate a stimulus from the second table. And we have, you can see the bars inside the table look different from the other ones because I use a gray values instead of just black and white to denote a continuous value between 0 and 1. So suppose here you have like 0.2, like this value is 0.2, then it means if we sample from it, it's just a Bernoulli random variable. Like if we sample from this, then this dimension, there is a 0.2 probability to get 1 and 0.8 probability to get 0. Right. Okay, finally we got the easiest understood word. Okay, so you have a set of parameters to generate the variable, the random variable. Like this. You sample from this. Like we have made a very simple assumption as Anderson did, like these 5 dimensions, they are independent. So you just make independent sampling from them. So you may get something like this. Okay, so this is one possibility. Actually, the new customer may join an existing table like table 2 and also is likely to join the table 1. And it may also come to a new table. So what will happen in this case? Because now you see there's nothing inside the new table. So if this happens, then there is a hyperprior for the prototype or the set of parameters inside this table. Like here is we could use a beta distribution to generate random values here. So what I will show here is just trying the special case of the beta distribution. As you know, the beta 1 is just a uniform distribution. So it's like for each value here, you just pick a random value, a uniformly random value from between 0 and 1 and put it here, likely for this. And then you generate the new variables from these parameters, just like you did before for the existing tables. Okay. So after we get the generative process, what's the Bayesian inference? The problem is the observer see stimuli come in a sequence one by one, and the observer needs to categorize them, which means to assign them to different tables if we just equalize the table with the category. So this is what exactly Anderson did in his 1991 paper. Strictly speaking, he was not doing strictly Bayesian. He knows that what he tried to do is to do approximate algorithm for this kind of Bayesian inference. So we can go over some of the commutations just to be familiar with this kind of process. How much time do I have? 5 minutes or 10 minutes?
You have 25 minutes, but of course we can have questions. So whenever you want to finish.
Okay. I'm just trying to be sure whether you understood all of this, or so this page will just illustrate how these commutations likely happen in exactly the Anderson way. So what we see here is we have some assumptions like we just saw, like assume alpha equals 1, and the value of each category on each dimension is samples from a beta distribution of 1, a uniform distribution. So now we see the stimuli come one by one. The same first stimulus is 1, 1, 1, 1, 1, or the ones on the or the dimensions. We could compute a likelihood to observe this kind of stimulus, but I think we can just move on to the second stimulus, because the first stimulus, of course, it will go into just a one category by itself, and then we see a second stimulus look like this. Then where should it go? There are two possibilities. One is to join the first stimulus. The second one is to create a new category by itself. So what would be the posterior probabilities for these two possibilities? It works like this. We know that the prior probabilities for the actually I would say the priors for the stimuli in the first category before we observe any stimuli, it looked like this. I mean you have a 1.5 probability to observe a 1 and a 1/2 probability to observe a 0. And then after we already have observed this stimulus, then you would update the values in this category like this. It's actually it's just a kind of beta. You just update, because this process is a conjugate, the beta works as conjugate prior. Beta is just like it's like the coin tossing problem. Like suppose before you toss any coin, you think the probability for you to toss a head and a tail would be 1 and 1. Then after you observed a 1 head, then you would add to the head thing. Then you would think, oh, the posterior probability for me to get head would be 2/3. Yeah, it like this. So you would update this probability, and based on this, you could compute what's the posterior for the probability that I would observe this stimulus, the stimulus 2 in the same category. It's just a Bayesian formula. Well, I know it would be better if I derive it on the fly, but the problem is I'm not very good at it, so it would be some risk that I make some mistakes. So I just show it here. So you just follow this formula and you can get the answer. And if you don't believe it, you could just check it yourself. Oh, okay. Actually, to check itself is just very good practice. This is also what I did when I read Anson's paper to make sure I understood it. Okay. So if you goes to another possibility, then it comes with a different category. Then you could similarly compute what's the posterior probability that this second stimulus goes to a new